Okay, now we're going to be doing arithmetic sequences of the quadratic type. By the end of this, we're going to have filled in an equation in this block here. In fact, I'm going to start off right away by telling you what that equation is. For the arithmetic sequences of the quadratic type, we're going to have the general formula of Tn is equal to an squared plus bn plus c. Right? Let's now go ahead and prove that this works. To do that, we're going to do Tn for n is 1 to n is 2, n is 3, and n is 4. Let's first sub in n is 1. What we're doing, we get a plus b plus c. What we've done here is we simply subbed in 1 for n is 1, and n is 1 over here, and we know 1 squared is 1, and b times 1. That's great. Now let's go along, n is 2, and we know that a times 2 squared is 4a, plus 2b plus c, and we go ahead for n is 3, 9a plus 3b plus c, and n is 4. Right? Now let's check the first difference of this sequence. Now we know that if the first difference is constant, like we had previously, then this will be a linear arithmetic series. But let's check that first difference. So to do that, we go 4a minus 4 minus a, and that gives us 3a. 2b minus b is just b, and c minus c cancels each other out. Now let's check the next one. 9a minus 4a, that's 5a. 3b minus 2b, that's 1b. And c minus c, that goes away. So it's 5a plus 2b, plus b. This immediately tells us these are different. This cannot be a linear type arithmetic sequence because the first difference is not constant. So let's go ahead and check now the last one, and this is 7a plus b. Now what we're going to do is we're going to check the second difference of these equations. So let's go 5a minus 3a, that's 2a, b minus b is 0. Let's go 7a plus b minus 5a plus b, the b's cancel, and we get 7a minus 5a, that's 2a. And now we have a second constant difference. And you do that on, and you keep going on, you extend the sequence, and you'll find that these stay 2a right the way through. And this is how we've just proved a quadratic second difference, second difference formula. Let's just go through an example. Let's have a block of size 1, a block of size 4 blocks, 9 blocks, 16 blocks, and 25 blocks. As you can see, we keep changing the length of each side. But here we have a sequence, 1, 4, 9, 16, 25. Let's see what the difference between those sequences are. 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 9 is minus 16 is 9. Again, there's not a constant first difference, so this cannot be a linear arithmetic sequence. So the first difference here has shown that it's not constant. So let's have a look at the second difference. Let's go right ahead and say that's 5 minus 3 is 2, 7 minus 5 is 2, 9 minus 7 is 2. That's perfect. This shows us an arithmetic sequence. So let's take that formula and put it that sequence and put it into one of our tables where we have T1, T2, T3, T4, and T5. Remembering the ends. Now we know the difference. 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 16 is 9. We already worked it out. Let's calculate the second difference. 5 minus 3 is 2, and that's etc. what we did on the last slide. Now we found ourselves a bit of a pattern. If we take n and we square it, we get 1. If we take n and we square it again, we get 4. If we take n and we square it, 3 squared, we get 9, and we find that this is a pattern. So from here we can figure out what this formula is for this example. And we find that the general formula for this example only is n squared. Let us not forget, you might be wondering where's the b, the c, the a, the b, and the c. Well, if you look right here, you can find that this is from the general formula an squared plus bn plus c, where a is 1, b is 0, and c is 0. And this is our general formula, and here is an example of it. Well done. Now we can fill in a quadratic formula here. And that's what we have in our arithmetic sequences, quadratic formulas. Next we're going to go on to geometric sequences. Great.